So kind of one picture that you can have in mind when we're doing SGD plus momentum is that the red here is our current point. At our current point, we have some red vector, which is the direction of the gradient, or rather our estimate of the gradient at the current point. And green is now the direction of our velocity vector. And now when we do the momentum update, we're actually stepping according to a weighted average of these two. And this helps overcome some noise in our gradient estimate. There's a slight variation of momentum that you sometimes see called a Nesterov accelerated gradient, also sometimes called Nesterov momentum, that switches up this order of things a little bit. So in sort of normal SGD momentum, we imagine that we estimate the gradient at our current point and then take a mix of our velocity and our gradient. With Nesterov accelerated gradient, you do something a little bit different. Here, you start at the red point. You step in the direction of where the velocity would take you. You evaluate the gradient at that point, and now then you go back to your original point and kind of mix together those two. So this is kind of a funny interpretation, but you can imagine that you're kind of mixing together information a little bit more. That maybe if your velocity direction was actually a little bit wrong, it lets you incorporate gradient information from a little bit larger parts of the objective landscape. This also has some really nice theoretical properties when it comes to convex optimization, but those guarantees go a little bit out the window once it comes to non-convex problems like neural networks. So writing it down in equations, Nesterov momentum looks something like this, where now to update our velocity, we take a step according to our previous velocity and evaluate the gradient there. And now when we take our next step, we mix together, we actually step in the direction of our velocity that's incorporating information from these multiple points. Yeah, so intuitively, the velocity is kind of a weighted sum of your gradients that you've seen over time. Yes, with more recent gradients being weighted heavier. So at every time step, we take our old velocity, we decay by friction, and we add in our current gradient. So you can kind of think of this as a smooth moving average of your recent gradients with kind of an exponentially decaying weight on your gradients going back in time. So this Nesterov formulation is a little bit annoying, because if you look at this, normally when you have your loss function, you want to evaluate your loss and your gradient at the same point, and Nesterov breaks this a little bit, so it's a little bit annoying to work with. Thankfully, there's a cute change of variables you can do. So if you do the change of variables and reshuffle a little bit, then you can write Nesterov momentum in a slightly different way that now, again, lets you evaluate the loss and the gradient at the same point always. And once you make this change of variables, you get kind of a nice interpretation of Nesterov, which is that here in the first step, this looks exactly like updating the velocity in the vanilla SGD momentum case, where we have our current velocity, we evaluate gradient at the current point, and mix these two together in a decaying way. And now in the second update, and now when we're actually updating our parameter vector, if you look at the second equation, we have our current point plus our current velocity plus a weighted difference between our current velocity and our previous velocity. So here, Nesterov momentum is kind of incorporating some kind of error-correcting term between your current velocity and your previous velocity. And if you look at what these, so if we look at SGD momentum, and Nesterov momentum on this kind of simple problem, compared with SGD, we notice that Nesterov and so SGD kind of takes this, SGD is in the black, kind of taking this slow progress toward the minima. The blue and the green show momentum and Nesterov, and these have this behavior of kind of overshooting the minimum because they're building up velocity, going past the minimum, and then kind of correcting themselves and coming back towards the minima. Yeah, so the question is like this picture looks good, but what happens if your minima lies in this like very narrow basin? Will the velocity just cause you to skip right over that minima? That's actually a really interesting point and the subject of some recent theoretical work. But the idea is that maybe those really sharp minima are actually bad minima. We don't want to even land in those. Because the idea is that maybe if you have a very sharp minima, that actually could be a minima that overfits more. That if you imagine that we doubled our training set, the whole optimization landscape would change, and maybe that very sensitive minima would actually disappear if we were to collect more training data. So we kind of have this intuition that we maybe want to land in very flat minima, because those very flat minima are probably more robust as we change the training data. So those flat minima might actually generalize better to testing data. So this is, again, like sort of very recent theoretical work, but that's actually a really good point that you bring it up. So in some sense, it's actually a feature and not a bug that SGD momentum actually skips over those very sharp minima. And so that's actually a good thing, believe it or not. But another thing you can see is if you look at the difference between momentum and Nesterov here, you can see that because of the correction factor in Nesterov, maybe it's not overshooting quite as drastically compared to vanilla momentum. So there's another kind of common optimization strategy is this algorithm called Adagrad, which John Ducci, who's now a professor here, worked on during his PhD. And the idea with Adagrad is that as you go during the course of the optimization, you're going to keep a running estimate or a running sum of all the squared gradients that you see during training. So now, rather than having a velocity term, instead we have this grad squared term. And during training, we're going to just keep adding the squared gradients to this grad squared term. And now, when we update our parameter vector, we'll divide by this grad squared term when we're making our update step. And the question is, what does this kind of scaling do in this situation where we have a very high condition number? Yeah, so the idea is that if we have two coordinates, one that always has a very high gradient and one that always has a very small gradient, then as we add the sum of the squares of the small gradient, we're going to be dividing by a small number. So we'll accelerate movement along the slow dimension, along the one dimension, and then along the other dimension where the gradients tend to be very large, then we'll be dividing by a large number. So we'll kind of slow down our progress along the wiggling dimension. But there's kind of a problem here, and that's the question of what happens with Adagrad over the course of training, like as t gets larger and larger and larger. Yeah, so with Adagrad, the steps actually get smaller and smaller and smaller because we just continue updating this estimate of the squared gradients over time. So this estimate just grows and grows and grows monotonically over the course of training. And now this causes our step size to get smaller and smaller and smaller over time. Again, in the convex case, there's some really nice theory showing that this is actually really good, and that kind of because in the convex case, as you approach a minimum, you kind of want to slow down, so you actually converge. So that's actually kind of a feature in the convex case. But in the non-convex case, that's a little bit problematic because then as you come towards a saddle point, you might get stuck with Adagrad, and then you kind of no longer make any progress. So there's a slight variation of Adagrad called RMS prop that actually addresses this concern a little bit. So now with RMS prop, we still keep this estimate of the squared gradients, but instead of just letting that squared estimate continually accumulate over training, instead we let that squared estimate actually decay. So this ends up looking kind of like a momentum update, except we're having kind of momentum over the squared gradients rather than momentum over the actual gradients. So now with RMS prop, after we compute our gradient, we take our current estimate of the grad squared, we multiply it by this decay rate, which is commonly something like 0.9 or 0.99. Then we add in this 1 minus the decay rate of our current squared gradient. So now, over time, you can imagine that and then again, when we make our step, the step looks exactly the same as Adagrad, where we divide by the squared gradient in the step to again have this nice property of accelerating movement along one dimension and slowing down movement along the other dimension. But now with RMS prop, because these estimates are leaky, then it kind of addresses the problem of maybe always slowing down where you might not want to. And if you plot, here again, we're kind of showing our favorite toy problem with SGD in black, SGD momentum in blue, and RMS prop in red. And you can see that RMS prop and SGD momentum are both doing much better than SGD, but their qualitative behavior is a little bit different. So with SGD momentum, it kind of overshoots the minimum and comes back. Whereas with RMS prop, it's kind of adjusting its trajectory such that we're making approximately equal progress among all the dimensions. And by the way, you can't actually tell, but this plot is also showing Adagrad in green with the same learning rate, but it just gets stuck due to this problem of continually decaying learning rates. So in practice, Adagrad is maybe not so common for many of these things. So that's a little bit of an unfair comparison with Adagrad, because probably you need to increase the learning rate with Adagrad, and then it would end up looking kind of like RMS prop in this case. But in general, we tend not to use Adagrad so much when training neural networks. Question? Yeah, so the answer is yes, this problem is convex. But in this case, it's a little bit of an unfair comparison because the learning rates are not so comparable among the methods. So I've been a little bit unfair to Adagrad in this visualization by showing the same learning rate between the different algorithms, when probably you should have separately turned the learning rates per algorithm. So this is kind of working towards, so we saw in momentum, we had this idea of velocity, where we're building up velocity by adding in the gradients and then stepping in the direction of the velocity. And we saw with Adagrad and RMS prop that we had this other idea of building up an estimate of the squared gradients and then dividing by the squared gradients. So then, like, these both seem like good ideas on their own. Why don't we just stick them together and use them both? Maybe that would be even better. And that brings us to this algorithm called ATOM, or rather brings us very close to ATOM. We'll see in a couple slides that there's a slight correction we need to make here. So here with ATOM, we maintain an estimate of the first moment and the second moment. And now in the red, we make this estimate of the first moment as a weighted sum of our gradients. And we have this moving estimate of the second moment, like Adagrad and like RMS prop, which is a moving estimate of our squared gradients. And now when we make our update step, we step using both the first moment, which is kind of our velocity, and also divide by the second moment, or rather the square root of the second moment, which is this squared gradient term. So this idea of ATOM ends up looking a little bit like RMS prop plus momentum, or ends up looking like momentum plus second squared gradients. So it kind of incorporates the nice properties of both. But there's a little bit of a problem here, and that's the question of what happens at the very first time step. So at the very first time step, you can see that at the beginning, we've initialized our second moment with 0. And now, after one update of the second moment, typically this beta 2 second moment decay rate is something like 0.9 or 0.99, like something very close to 1. So after one update, our second moment is still very, very close to 0. So now when we're making our update step here and we divide by our second moment, now we're dividing by a very small number. So we're making a very, very large step at the beginning. And this very, very large step at the beginning is not really due to the geometry of the problem. It's kind of an artifact of the fact that we initialized our second moment estimate with 0. That's true. The comment is that if your first moment is also very small, then you're like multiplying by small and you're dividing by square root of small squared. So like, what's going to happen? They might cancel each other out. You might be okay. That's true. So sometimes these cancel each other out and you're okay. But sometimes this ends up in taking very large steps right at the beginning. And that can be quite bad. And that can, maybe you initialize a little bit poorly. You take a very large step. Now your initialization is completely messed up. And then you're in a very bad part of the objective landscape. And you just can't converge from there. Yeah, so the idea is, what is this 10 to the minus 7 term in the last equation? So that's actually appeared in Adagrad, RMS prop, and ATOM. So the idea is that we're dividing by something. We want to make sure we're not dividing by 0. So we always add a small positive constant to the denominator, just to make sure we're not dividing by 0. That's technically a hyperparameter, but it tends not to matter too much. So just setting 10 to minus 7, 10 to minus 8, something like that tends to work well. So with ATOM, remember we just talked about this idea of at the first couple steps, it gets very large, and we might take very large steps and mess ourselves up. So ATOM also adds this bias correction term to avoid this problem of taking very large steps at the beginning. And so you can see that after we update our first and second moments, we create an unbiased estimate of those first and second moments by incorporating the current time step t. And now we actually make our step using these unbiased estimates rather than the original first and second moment estimates. So this gives us our full form of ATOM. And by the way, ATOM is a really, really good optimization algorithm, and it works really well for a lot of different problems. So that's kind of my default optimization algorithm for just about any new problem that I'm tackling. And in particular, if you set beta 1 equals 0.9, beta 2 equals 0.999, learning rate 1e minus 3 or 5e minus 4, like that's a great starting point for just about all the architectures I've ever worked with. So like try that. If it doesn't, like that's a really good place to start in general. So if we actually plot these things out and look at SGD momentum, RMS prop, and ATOM on the same problem, you can see that Atom in the purple here kind of combines elements of both SGD momentum and RMS prop. So Atom kind of overshoots the minimum a little bit like SGD momentum, but it doesn't overshoot quite as much as momentum. Atom also has this similar behavior of RMS prop of kind of trying to curve to make equal progress along all dimensions. And maybe in this small two-dimensional example, Atom converged about similarly to other ones. But you can see qualitatively that it's kind of combining the behaviors of both momentum and RMS prop. The question is, what does Atom not fix? With these neural networks are still large, they still take a long time to train. So there can still be a problem. So in this picture where we had this landscape of things looking like ovals, if you imagine that we're kind of making estimates along each dimension independently to allow us to speed up or slow down along different coordinate axes. But one problem is that if that taco shell is kind of tilted and is not axis aligned, then we're still only making estimates along the individual axes independently. And that corresponds to kind of like taking your rotated taco shell and squishing it horizontally and vertically, but you can't actually unrotate it. So in cases where you have this kind of rotated picture of poor conditioning, then Atom or any of these other algorithms really can't address that concern. So another thing that we've seen in all these optimization algorithms is learning rate as a hyperparameter. So we've seen this picture before a couple times that as you use different learning rates, sometimes if it's too high, it might explode in the yellow. If it's a very low learning rate in the blue, it might take a very long time to converge. And it's kind of tricky to pick the right learning rate. But this is a little bit of a trick question because we don't actually have to stick with one learning rate throughout the course of training. Sometimes you'll see people decay the learning rates over time, where we can kind of combine the effects of these different curves on the left and get the nice properties of each. So sometimes you'll start with a higher learning rate near the start of training and then decay the learning rate and make it smaller and smaller throughout the course of training. A couple strategies for these would be a step decay, where like at 100,000 iteration, you just decay and by some factor and you keep going. You might see an exponential decay where you continually decay during training. Or you might see, so you might see different variations of kind of continually decaying the learning rate during training. And if you look at papers, especially the ResNet paper, you often see plots that look kind of like this, where the loss is kind of going down, then dropping, and then flattening again, then dropping again. And what's going on in these plots is that they're using a step decay learning rate, where at these parts where it plateaus and then suddenly drops again, those are the iterations where they dropped the learning rate by some factor. So this idea of dropping the learning rate kind of let it escape. You might imagine that it got near some good region, but now the gradients got smaller. It's kind of bouncing around too much. And then if we drop the learning rate, it lets it slow down and continue to make progress down the landscape. So this tends to help in practice sometimes. Although one thing to point out is that learning rate decay is a little bit more common with SGD momentum and a little bit less common with something like Atom. Another thing I'd like to point out is that learning rate decay is kind of a second-order hyperparameter. You typically should not optimize over this thing from the start. Usually, when you're kind of getting networks to work at the beginning, you want to pick a good learning rate with no learning rate decay from the start, and trying to cross-validate jointly over learning rate decay and initial learning rate and other things, you'll just get confused. So what you do for setting learning rate decay is try with no decay, see what happens, and then kind of eyeball the loss curve and see where you think you might need decay. So another thing I wanted to mention briefly is this idea of all these algorithms that we've talked about are first-order optimization algorithms. So in this picture, in this one-dimensional picture, we have this kind of curvy objective function, and at our current point in red, what we're basically doing is computing the gradient at that point. We're using the gradient information to compute some linear approximation to our function, which is kind of a first-order Taylor approximation to our function. And now we pretend that the first-order approximation is our actual function, and we make a step to try to minimize the approximation. But this approximation doesn't hold for very large regions, so we can't step too far in that direction. But really, the idea here is that we're only incorporating information about the first derivative of the function. And you can actually go a little bit fancier. And there's this idea of second-order approximation, where we take into account both first derivative and second derivative information. And now we make a second-order Taylor approximation to our function and kind of locally approximate our function with a quadratic. And now with a quadratic, you can step right to the minimum, and you're really happy. And that's this idea of second-order optimization. So when you generalize this to multiple dimensions, you get something called the Newton step, where you compute this Hessian matrix, which is a matrix of second derivatives, and you end up inverting this Hessian matrix in order to step directly to the minimum of this quadratic approximation to your function. So does anyone spot something that's quite different about this update rule compared to the other ones that we've seen? Yeah, so this doesn't have a learning rate. That's kind of cool. Because we're making this quadratic assumption, we're making this quadratic approximation, and we're stepping right to the minimum of the quadratic. So at least in this vanilla version of Newton's method, you don't actually need a learning rate. You just always step to the minimum at every time step. However, in practice, you might end up have a learning rate anyway, because again, that quadratic approximation might not be perfect. So you might only want to step in the direction towards the minimum rather than actually stepping to the minimum. But at least in this vanilla version, it doesn't have a learning rate. But unfortunately, this is maybe a little bit impractical for deep learning, right? Because this Hessian matrix is like n by n, where n is the number of parameters in your network. So if n is like 100 million, then 100 million squared is way too big. You definitely can't store that in memory, and you definitely can't invert it. So in practice, people use these quasi-Newton methods that rather than working with the full Hessian and inverting the full Hessian, they work with approximations. Low-rank approximations are common. So you'll sometimes see these for some problems. LBFGS is one particular second-order optimizer that has this approximate keeps this approximation to the Hessian that you'll sometimes see. But in practice, it doesn't work too well for many deep learning problems because these approximations, these second-order approximations, don't really handle the stochastic case very nicely, and they also tend not to work so well with non-convex problems. I don't want to get into that right now too much. So in practice, what you should really do is probably Atom is a really good choice for many different neural network things. But if you're in a situation where you can afford to do full batch updates and you know that your problem doesn't have really any stochasticity, then LBFGS is kind of a good choice. So LBFGS doesn't really get used for training neural networks too much. But as we'll see in a couple lectures, it does sometimes get used for things like style transfer, where you actually have less stochasticity and fewer parameters. But you still want to solve an optimization problem. So all of these strategies we've talked about so far are about reducing training error, right? And all these optimization algorithms are really about driving down your training error and minimizing your objective function. But we don't really care about training error that much. Instead, we really care about our performance on unseen data. We really care about reducing this gap between train and test error. So the question is, once we're already good at optimizing our objective function, what can we do to try to reduce this gap and make our model perform better on unseen data? So one really quick and dirty, easy thing to try is this idea of model ensembles that sometimes works across many different areas in machine learning. So the idea is pretty simple. Rather than having just one model, we'll train like 10 different models independently from different initial random restarts. And now at test time, we'll run our data through all of the 10 models and average the predictions of those 10 models. And this tends to, adding these multiple models together tends to reduce overfitting a little bit and tends to improve performance a little bit, typically by a couple %. So this is generally not a drastic improvement, but it is a consistent improvement. And you'll see that in competitions like ImageNet and other things like that, using model ensembles is very common to get maximal performance. But you can actually get a little bit creative with this. And sometimes, rather than training separate models independently, you can just keep multiple snapshots of your model during the course of training and then use these as your ensembles. So then you still, at test time, need to average the predictions of these multiple snapshots. But you can collect the snapshots during the course of training. And there's actually a very nice paper being presented at iClear this week that kind of has a fancy version of this idea, where we use a crazy learning rate schedule, where our learning rate goes like very slow, then very fast, then very slow, then very fast. And the idea is that with this crazy learning rate schedule, then over the course of training, the model might be able to converge to different regions in the objective landscape that all are reasonably good. And now if you make ensemble, and then if you do an ensemble over these different snapshots, then you can improve your performance quite nicely, even though you're only training the model once. The question is it's bad when there's a large gap between error, because that means you're overfitting. But if there's no gap, then is that also maybe bad? And do we actually want some like small optimal gap between the two? So we don't really care about the gap. What we really care about is the maximizing the performance on the validation set. So what tends to happen is that if you don't see a gap, then you could have improved your absolute performance in many cases by reducing the overfit, by overfitting a little bit more. So there's this weird correlation between the absolute performance on the validation set and the size of that gap. And we really care about absolute performance. Are the hyperparameters same for the ensembles? That's a good question. Sometimes they're not, right? Like you might want to try different sizes of the model, like different learning rates, different regularization strategies, an ensemble across these different things. That actually does happen sometimes.
지난 시간에 이어서 SGD 모멘텀에 대해서 알아보도록 하겠습니다. 기본적 아이디어는 그라디언트에 벨로시티 벡터를 더해서 액추얼 스텝 벡터를 얻도록 한 것입니다. 네스트롭 모멘텀은 SGD 모멘텀에 약간의 변화를 준 것입니다. 현재 스텝에서의 그라디언트보다 벨로시티를 고려한 다음 스텝에서의 그라디언트를 구하는 것입니다. 다음은 네스트롭 모멘텀의 이퀘이션입니다. 문제는 그라디언트 F의 아르규먼트인 xt 플러스 로 vt입니다. 알고리즘의 코딩을 위해서는 xt와 gradient f of xt의 형태로 표현하는 것이 좋습니다. 이를 위해서 xt 틸다는 xt 플러스 로 vt로 정의해서 식을 다시 rearrange 했습니다. 여기서 알파는 러닝 레이트이고 로는 프릭션, 마찰입니다. 다음은 SGD와 SGD 모멘텀 그리고 네스테로프 알고리즘을 비교한 결과입니다. 네스테로프가 가장 효율적으로 로스 미니멈에 접근하는 것을 볼 수 있습니다. 그러나 로스 미니멈을 지나쳐갔다 되돌아오는 것처럼 아직 개선할 점들이 있습니다. 또 다른 알고리즘으로 아다그레드가 있습니다. 이 알고리즘은 벨로시티 대신에 그레드 스퀘어드를 사용합니다. 트레이닝 동안에 스퀘어드 그라디언트를 이 그라디언트 스퀘어드 텀에 계속 더해 나갑니다. 그리고 업데이트 스텝을 만들 때 나눠주는 텀으로 사용됩니다. 우리는 아다그라드가 주어진 예제처럼 수평과 수직의 그라디언트가 크게 차이 날 때 어떻게 동작하는지에 대해 질문을 던질 수 있습니다. 아다그라드는 그라드가 작을 때에는 작은 값으로 나눠주고 그라드가 클 때는 큰 값으로 나눠주기 때문에 지터를 줄여주는 효과가 있습니다. 또한 긴 시간 동안에 스텝 사이즈가 어떻게 변화해 나가는지에 대해서도 질문할 수 있습니다. 시간이 진행될수록 그레드 스퀘어는 계속 증가하기 때문에 스텝 사이즈는 계속 감소하게 됩니다. 이는 랜드스케이프가 컨벡스일 경우에는 문제가 없는데 새들 포인트가 있는 경우 새들 포인트에서 갇혀버릴 수 있는 위험이 있습니다. 이러한 문제를 보완하기 위해서 아다그레드에 약간의 변화를 준 것이 RMS 프롭입니다. 그레드 스퀘어드가 계속해서 증가하는 것을 막기 위해서 decay rate이라는 변수를 지정합니다. 이것은 과거에 배웠던 모멘텀 아이디어와 유사한 점이 있습니다. 이 경우 액추얼 그라디언트가 아니라 스퀘어드 그라디언트에 대한 모멘텀을 활용한 것이라고 볼 수 있습니다. 다음은 SGD, SGD 모멘텀, RMS 프롭을 비교한 것입니다. RMS 프롭은 빨간색으로 표시되어 있는데 목표에 다가갈수록 스텝 사이즈가 줄어들기 때문에 SGD 모멘텀보다 목표에 느리게 도착하는 것을 볼 수 있습니다. 장점으로는 SGD 모멘텀보다 오버슈팅이 적다는 것을 들 수 있습니다. 또 다른 알고리즘으로 아담은 SGD 모멘텀과 RMS 프롭의 장점을 결합하도록 설계되었습니다. 먼저 dx 값을 x의 그라디언트로 어사인합니다. dx로부터 포스트 모먼트를 계산하고 dx 스퀘어로부터 세컨드 모먼트를 계산합니다. 마지막으로 포스트 모먼트와 세컨드 모먼트를 이용해서 x값을 이동시킵니다. 그러나 이 방법에는 약간의 문제점이 있습니다. 베타2는 0.9 혹은 0.99와 같은 1에 가까운 값이 사용되기 때문에 처음 타임 스텝에서 세컨드 모먼트가 너무 작아질 수 있습니다. 이런 문제를 해결하기 위해서 포스트 모먼트와 세컨드 모먼트에 바이어스 커렉션을 해줍니다. t가 증가함에 따라서 바이어스 커렉션의 효과는 줄어드는 것을 볼 수 있습니다. 여러 모델에서 아담을 실험한 결과 베타1이 0.9이고 베타2는 0.999, 러닝 레이트는 10-3승이나 5 곱하기 10-4승인 경우가 좋은 시작점이라는 것이 밝혀졌습니다. 다음은 SGD, SGD 모멘텀, RMS 프로, 아담을 비교한 것입니다. 이번 사례의 경우 아담은 초기에는 RMS 프로 같은 특성을 띠지만 후반부에는 SGD 모멘텀 같은 특성을 보여주고 있습니다. 그러나 SGD 모멘텀과 달리 목표 지정 부근에서 오버슈팅이 감소했습니다. SGD와 아담을 비롯한 모든 알고리즘들은 러닝 레이트를 하이퍼 파라미터로 갖고 있습니다. 왼쪽 그래프를 보면 하이 러닝 레이트 경우에 처음에는 빨리 감소하지만 어느 정도가 지나면 러닝이 이루어지지 않는 것을 볼 수 있습니다. 반면에 로우 러닝 레이트는 로스가 천천히 감소하지만 꾸준히 감소하는 것을 볼 수 있습니다. 제일 바람직한 것은 로우 러닝 레이트와 하이 러닝 레이트 사이에 있는 굿 러닝 레이트를 발견하는 것입니다. 러닝 레이트를 시간에 따라 감소시키는 방법도 사용됩니다. 스텝 디케이는 few 에포크마다 러닝 레이트를 반으로 줄이는 것입니다. 익스포넨셜 디케이는 익스포넨셜 함수로 감소시키는 것입니다. 1/t 디케이는 1 플러스 kt로 나눠주는 것입니다. 러닝 레이트 디케이를 실행하는 방법 중 하나는 오른쪽 그림에 나타난 것처럼 로스 값의 감소가 어느 정도 정체되었을 때마다 러닝 레이트 디케이를 실행하는 것입니다. 러닝 레이트 디케이는 아담보다는 SGD 모멘텀에서 더욱 중요합니다. 지금까지 언급된 알고리즘들은 포스트 오더 옵티마이제이션을 기본으로 한 것입니다. 이 그래프는 로스를 W1의 함수로 나타낸 것입니다. 빨간 점은 현재의 위치입니다. 첫 번째로 그라디언트를 사용해서 리니어 어프록시메이션을 합니다. 두 번째로 어프록시메이션을 미니마이즈하는 스텝을 수행합니다. 이번에는 세컨 오더 옵티마이제이션에 기반한 알고리즘에 대해서 알아보겠습니다. 첫 단계는 그라디언트와 헤시안, 즉 2차 편미분을 사용해서 쿼드래틱 2차 방정식 어프록시메이션을 합니다. 여기서 2차 방정식은 그래프에서 파란 선으로 표시되어 있습니다. 두 번째 단계는 어프록시메이션의 미니마로 스텝을 수행합니다. 그래프에서는 붉은 화살표로 점의 이동이 표시되어 있습니다. 이것은 세컨 오더 옵티마이제이션을 테일러 엑스펜션을 사용해서 다차원에서 구현한 것입니다. 이를 통해서 뉴턴 스텝이라고 부르는 파라미터를 업데이트하는 식을 얻습니다. 여기서 H는 헤시안 매트릭스인데 2차 편미분 행렬을 뜻합니다. 이 업데이트의 장점은 쿼드래틱 어프록시메이션의 미니멈으로 바로 스텝을 취할 수 있다는 점입니다. 따라서 러닝 레이트를 조절하는 프로세스가 필요 없게 됩니다. 그러나 문제점은 딥 러닝에서는 헤시안 매트릭스가 지나치게 커지기 때문에 실제로 구현하기가 어렵습니다. 따라서 쿼지 뉴턴 방식인 Limited Memory BFG를 사용해서 컴퓨팅과 메모리를 크게 줄인 근사적 방식을 사용합니다. 실제 적용에서 애담은 대부분의 경우에 좋은 디폴트 초이스입니다. 만약 풀 배치 업데이트를 할 수 있다면 LBFGS를 시도해 볼 수 있습니다. 비욘드 트레이닝 에러는 트레이닝 에러를 줄이는 것을 넘어서서 또 무엇을 할 수 있는가를 알아보는 것입니다. 오른쪽 그래프를 보면 트레인 데이터의 애큐러시보다 밸리데이션 데이터의 애큐러시가 낮은 것을 알 수 있습니다. 우리의 관심은 어떻게 밸리데이션 데이터의 애큐러시를 증가시켜서 그 갭을 줄일 수 있는가 하는 것입니다. 모델 앙상블을 사용하면 2%의 엑스트라 퍼포먼스를 얻을 수 있습니다. 첫 번째로 다수의 인디펜던트 모델을 트레인합니다. 두 번째로 그들의 결과를 테스트 타임에서 에버리지합니다. 모델 앙상블을 구현하는데 트릭을 사용할 수도 있습니다. 다수의 독립적 모델을 트레이닝하는 것은 큰 비용이 들기 때문에 하나의 모델을 사용해서 멀티플 스냅샷을 취하도록 하는 것입니다.